In phrasing the mysteries of a universe, we often phrase it as surprising that most of the energy budget of the universe is dark, and that components of the universe that we know exist, like you and me, and all of the standard matter, and stars and black holes, etc., only make 5% of the energy budget of the universe. But the real question to my mind, the real puzzle to my mind, is not why is the universe so dark? The real question is why isn't it much darker? Why is vacuum energy not accounting for a much larger proportion of the energy budget of the universe as we would have expected? And faced with the biggest discrepancy in the whole history of humanity, I would say, the standard approach that you may hear of is simply to ignore the elephant in the room. This problem is so big that I'm simply not going to look at it. Maybe it's just going to go away. I'm just going to postulate for a reason or another that this whole hugeness of vacuum energy does not exist. I'm going to set it to 0 for an unknown reason that future generations are going to tell me. And instead, I'm going to postulate the existence of another, new kind of dark energy fluid, which has properties, actually, at the classical level that would have very similar properties to this vacuum energy. And that is the new driver for the cosmic acceleration of the universe. So that is one approach. And I'm going to go a bit crazy. But for the last few minutes, I'll try to postulate a slightly different approach. I like to go directly at the core of this problem. And I like to allow myself to consider this vacuum energy, which should be present, actually driving the acceleration expansion of the universe. Because it is there, it is naturally there. And so what I need to do is explain why this vacuum energy doesn't have as large an effect on the evolution of the universe as what I would have expected according to Einstein's theory of general relativity. In Einstein's theory of general relativity, we say that gravity has an infinite reach. This means that if I consider two objects located very far away from one another, let me just imagine two galaxies located on the other side of the observable universe from one another, some 10,000 million trillion kilometers away from one another. In Einstein's theory of general relativity, they still technically exert a small gravitational attraction on each other. Gravity is diluted more or less according to Einstein's square law, so there is a dilution there, but gravity never switches off entirely in Einstein's theory of general relativity. What's even more remarkable is that in order to describe the whole evolution of the universe, I need to account all of this vacuum energy that fills every pocket of the universe, and it is this huge effect that leads to this 28 orders of magnitude discrepancy between observations and expectations. But maybe this is just too much to ask. Could it be that gravity actually doesn't have an infinite reach, and I don't need to take all of this vacuum energy into account? If gravity had a finite reach, I would only need to account for a small proportion of this vacuum energy leading to the accelerated rate expansion of the universe. This range of gravity still has to be large. It still has to encompass the whole of the solar system, and the whole of the galaxy, and the whole of a local cluster of galaxy, but not an infinite range in itself. And having a phenomenon in nature that has a finite range, as I would like it to be here, is something that does happen. It is something that we have experienced in nature. The weak force in nature is a phenomenon that has a finite range, actually. It's a very natural perspective to have. In fact, the idea that gravity itself could have a finite range has been explored to some extent by many different scientists throughout the centuries. Newton himself contemplated the possibility that gravity, as he had it, could have a finite range. And Laplace after him, and many other scientists. And when people understood that gravity was through the manifestation of the curvature of space-time according to Einstein's theory of general relativity, and it had to be embedded into a quantum framework, people started exploring this possibility in that framework as well, including Pauli, who can be considered as one of the fathers of quantum physics, contemplated the possibility of having gravity in an Einstein sense, in a quantum sense also being a phenomenon with a finite reach. And this has happened throughout the past centuries, including Salam himself, who can be seen as one of the founders of the standard model of particle physics, one of the discoverers of the electroweak unification and the weak force, contemplated the possibility that gravity could have a finite reach. But this possibility has always been completely refuted, not because it wasn't consistent with observations, quite the opposite. Considering a theory of gravity which have a finite reach would actually help us reconcile our expectations with our observations of the accelerated rate of expansion of the universe. It was because it was impossible to make it work theoretically. It was plagued with discrepancies which didn't seem to make sense in themselves until these two gentlemen came along, Gregory Gabadazzi and Andrew Tolley. And then with them, we managed to engineer a new architecture for gravity, a new model, which could, in some sense, displace all of these pathologies that were present in the other models. Now, the subtleties of that models are a little bit technical for right now. Maybe some of those equations will tell you something. But in a sense, the architecture of this model is not so dissimilar to what you can think of Penrose stairs or those type of Escher drawing of stairs, impossible stairs. What happens there is that you live in a confined space, and what we needed to do for a theory of gravity with a finite reach is to confine all of the pathologies in a confined, constrained space so they can do no harm. Of course, it's a little bit more technical than that, but that's the essence of it. In my mind, the trick in itself was pretty cute, but we soon came to realize that it wasn't sufficient to come with one mathematical proof that a model was consistent. To be sure, mathematics don't lie, and so if you come with one mathematical proof, then it must be correct. But even in science, there's as many languages and culture and different mathematical ways of phrasing things as there are individuals. And so over the years, every time someone came along with a different perspective, a different language, we had to adapt our logic into their way of thinking. We had to translate a mathematical language into a different one. And we had to repeat that over the years again and again and again until every single way to phrase the problem was consistent with our way of thinking about theory of gravity. But addressing that question in itself was never really the aim. The real aim in a theory of gravity is to confront it with observations. And if we are lucky, in the next few years, and maybe a decade or two, our understanding of gravity and observations on the nature of gravity will be so precise that we may be able to discriminate between a theory of Einstein's theory of general relativity, where gravity has an infinite reach, and a theory of gravity which has a finite reach, or which interacts slightly differently to account for dark energy. For instance, if you consider two stars or two black holes merging, they emit gravitational waves which distort space and time, and they travel for millions of years before reaching us on Earth. And we can detect them here on Earth. We have detected them already. Now, for a particular event, on the top is the type of signal that you may expect if gravity has an infinite reach, as would be the case in Einstein's theory of general relativity. And on the bottom is the type of signal you would expect if gravity had a finite reach, because gravitational waves of slightly different colors, of slightly different frequency, would travel ever so slightly differently, and so the signal we observe would appear more compressed. Now, by comparing what we would expect with what we actually observe, we could distinguish between a theory of gravity that has an infinite reach, as in Einstein's theory of general relativity, and a theory of gravity that has a finite reach. Whether the model of gravity that we have explored will survive those tests, we don't know yet. In a decade or so, we'll have very precise tests of gravity, for instance, thanks to the LISA space interferometer that you can see there, which will really allow us to understand gravity at a much precise level. Overall, whether a theory of massive gravity, the theory of gravity with a finite range that we have explored, and all sorts of different considerations, will be for future generations to tell. It's for them to tell whether they have any imprint on nature and any reason of being. But for now, I just want to contemplate the fact that just here, just right now, in this room, and I don't even know if it's day or dark anymore, and it can be sunny or raining, or sometimes it can be snowy in Canada, I've been told. There's gravitational waves reaching us all the time from the depth of the universe. And with them, they carry the most profound and remarkable messages. If we detect them, if we understand them, we may be able to understand if and how we connect with other objects located on the other side of the universe from us, some 10,000 million trillion kilometers away from us. Understanding those gravitational waves and the nature of gravity will allow us to better understand whether infinitely small fluctuations from emptiness that fill the whole of the universe uniformly from here on Earth to the middle of the cosmic voids lead to an evolution of the universe, help us understand the past of our universe, the present, and the fate of the universe, and everything living in it. So I'll stop here. Thank you.